Hi everyone, I will be presenting on the paper A Drone Carried Multi-Channel Synthetic Aperture Radar, or SAR, for Advanced Buried Object Detection. And I chose this topic because it applied to my last internship and potentially future job. I would work on PCB designs for both the receive and transmit modules for our radar system. So this would be choosing filters, impedance matching with our coax lines, power balancing, timing and control, etc. And the point of this paper is mostly hardware, and it's describing how to shrink down our SAR to be carried on a drone and still be effective in detecting buried objects, so IEDs or landmines. We've already learned a little bit about SAR through our lectures because it fits into the imaging category of radar. So there was search and detect, imaging, and tracking. And SAR fits into the slow time processing category in our data matrix as we create an image out of each pixel on the CPI level of processing. So basically its purpose is to create these 2D and 3D images while the radar antenna is moving to eventually create images with finer spatial resolution. This paper doesn't go into much background of SAR. The paper is mainly focused on how to fit the SAR to the constraints of a drone. So I used some other resources to provide a summary of how it works. And I know the recent lecture was put up by a professor too that goes into a lot of detail if you're more curious. So the image here that I have shows the radar mounted onto a satellite, which is a common application of SAR. But the image applies to aircrafts and ideally our UAV in this case. So because the antennas are moving, while the radar pulses, it combines the echoes from multiple pulses along that motion of the antenna, creating this larger synthesized aperture, which is where the name SAR comes from, which gives us a larger bandwidth and overall improving our resolution. It's completely independent from both our range and our frequency that we're using. So here's a quick visual of the goal of this paper before I go into more detail. Up here is the UAV or drone that is being used. And you can see we have the transmit and receive antennas. And then you can see the stacks of PCB modules mounted onto the drone. There's also a separate GPS module up here somewhere. And then the drone itself also has a camera, its own GPS module, power supply already on it. And there are two modes of operation of the drone. The first is detect mode, so that's over here. And this is where the drone flies straight across the scene, and this uses strip map SAR. This can either be mono or bistatic in that way. The second is identification mode, and this uses our spotlight SAR concept. So this is where the drone circles around the area of interest, and it can capture images with a higher spatial resolution. So with a lightweight and a low power system that is designed in this paper, the system is designed for a maximum of a 20-minute flight, and weighing, this drone weighs about 4 kilograms or about 8 pounds. So why are we using SAR for our buried object detection? SAR is primarily operated for airborne applications, specifically aircrafts or satellites with well-known trajectories. And because the drones have this more erratic flight path, it's a challenge to adapt the SAR processing for this type of flight path. So basically, we don't want any warped images in the end because of the drone's weird flight patterns. So the data processing can be adapted, and this is a viable solution. And you'd be able to use this technology more freely than you would when the radar is mounted on a plane or even on a ground-based system. So the background of this paper focuses on the fact that significant research has been done by DLR, which is a long German word that means German Aerospace Center. And this is for a ground-based vehicle. So this is polarimetric, multistatic, multi-angular, and multi-channel SAR, which is going to be called P3M SAR from now on. And this technology has a capability to detect buried objects from several meters distance up to a depth of about 20 centimeters. It has sufficient spatial resolution and clutter removal. It combines GPS, a camera, and other sensors on board to support that SAR image processing. So now we ask, could this system be used on a drone in the same way as a ground vehicle-based system? The design requirements for the vehicle-based P3M SAR are different from the drone. So they need to be adapted for the arbitrary flight patterns and smaller module that needs to be used for the drone. The P3M SAR uses multi-mode ultra-high frequency and ultra-wideband radar for that high spatial resolution for its object detection and effective clutter suppression. So we need this for our drone. The UAV design also needs to be compact. It needs to be easy to maintain and easy to mount, including all of the radar modules, antennas, the battery, the GPS, in addition to all of the weight that the drone already carries from its own onboard sensors. And also low power consumption is a priority. The battery and the GPS will be independent from one another on the drone, and this is for testing purposes so that we can test our system in the end without putting it on the drone first. And finally, they need a data link for the radar data, the drone camera for real-time processing, and this is for our proper 3D image processing in the end, or 2D. Here's a side-by-side comparison of the main elements of the ground vehicle SAR and the adapted version for the drone-based SAR. So the biggest change to note, other than obviously the drone being smaller, airborne, and having fewer antennas, is the type of transmit signal. So the transmit signal will be a modulated continuous wave rather than a pulsed radar. And I'll talk a little bit more about that signal and those signals in the next slides. Also, a DDS chip is used for the transmit signal rather than a commercial grade waveform generator in the existing system, and that DDS is direct digital synthesis chip. And overall, the output power for our drone-based system is about 250 milliwatts, which is good for an operational distance of about 15 feet. So there are 3 separate PCB modules that were put into this design: the transmit, the receive, and the signal generation, so that they could be stacked on top of one another on the drone more easily, and they could also be tested independently. And this is a common diagram that I would often see at work when designing the PCB boards at my work, so I thought it'd be interesting to include. This includes like frequency doublers, attenuators, amplifiers. There's a low noise amplifier that's used on the receive path, and some bandpass filters. And this is all for the up conversion in the transmit path and the down conversion in our received path. Another important aspect to talk about is the antennas that are going to be used for the system. The antenna system used for SAR, they're important because they affect the scene size, the spatial resolution, unambiguous ranges, and the range of detection. And our system will be using a Vivaldi antenna, and it's used to achieve that ultra wideband and achieve better range resolution. But the problem is these wide bands can cause strong variations in our antenna patterns and frequency response across the band, which has to be properly considered in the end when we're doing all of the processing for all the SAR processing. So now our transmit signal. The signal generator module is able to generate both frequency modulated continuous waves and stepped frequency continuous waves. And the experiments performed in this paper, the step frequency modulation is used. So we've seen the frequency modulation before, that's over here. we've seen that as time increases, we increase our frequency. So we have kind of this chirp on each pulse. And so when we're looking at the step frequency, it's a little different because as time goes on, we hold that frequency at a certain value and then step up our delta F. So we know how to handle our frequency modulations. We use match filters and things like that. In the end, our range is dependent on our difference frequency. So that's our difference from the mixing process of the linear modulation. But when we look over at step frequency, our range is dependent on our phase difference rather than our difference frequency. So next we talk about the proof of concept experiment that's performed to test the 3 modules. And this is a similar process that would be performed in the labs of my work to test the up converters and the down converters. So it's very simple. You basically just replace the antenna port with both the TX and the RX antenna ports with a coax line with an appropriate attenuation going directly from those 2 channels. And the length of this cable corresponds to the range of our simulated target. So as you can see from this range profile over here, we had a cable length of 10 meters, and after processing it, we approximately get 10 meters as our simulated target. And this just shows that our TX and our RX modules are working properly. So then we can move into a SAR measurement experiment. So this is where we're actually going to be moving our antennas. So if you've ever seen the setup in the MUMA radar labs next door with the big Motoman arms that hold the antenna and the microwave absorber chamber, this setup for this experiment is similar, except we have a linear motion axis right here that handles both the TX and the RX channels. So this motion is controlled enough to represent our ideal motion of our drone. And inside our microwave absorber chamber, we have 2 trihedral corner reflectors right here that are placed about 2.3 meters from those antennas and spaced apart 60 centimeters. And our results from this experiment are pretty clear. These are ideal conditions. We don't have to worry about the erratic movements of the drone, so the results are pretty clear. The measurements were taken as the antenna moved across the axis, and about 181 frequency profiles were recorded. And so the length of our synthetic aperture was about 1.8 meters, which gives them a range resolution of 6 centimeters and an azimuth resolution of 12.6 centimeters, which are both appropriate resolutions for our buried object detection application. So from the background research, designs, and results in this paper, it can be said that we have a couple of accomplishments. First of all, research was performed for a viable solution for our drone-based SAR. Second, they were able to design a lightweight radar system that was adapted from that P3M SAR, and it was successfully designed, including functioning receive, transmit, and signal modules. And it was able to generate that frequency modulated and that step frequency continuous wave as its operational modes with a sufficient output. And third, we had initial proof of concept testing that was successful in that controlled motion environment. So the complete drone-based SAR system is not functioning at this point. They just have it in those test conditions that we saw from the previous experiment. So really all I did in this paper was create a proof of concept ground model adapted from a well-researched ground vehicle-based P3M SAR. And so moving forward, there's a couple things that need to be done to complete the drone system. First of all, there needs to be a better understanding of the processing techniques for arbitrary UVA flight patterns. Precise knowledge of this flight path is needed for proper compensation in the SAR processing later on. And second, understanding the appropriate sensor design and data processing to sync all of the data together. So they still need to design a reference model for syncing all those sensors and the data acquisition board, which are both essential for the coherent synchronization of the raw radar data with an erratic flight pattern of a drone. So that is still under development. So thank you all for listening. Any questions are welcome if you want to send them to me. And other than that, here are my references, and thank you again.